Welcome everyone to this year's Zuriach Social Distancing Edition GHC track. I'm very happy that we have Richard Eisenberg here for the first talk this year. Please direct any questions to the GHC track channel. And without further ado, I'll be handing over to Richard. Thanks, Richard.
Yeah, hi everyone. It's so great to be back at Zuriach. Thanks for the invitation to come and give this talk. And just as a sort of a manner of bookkeeping here, just to be clear, so it's just newly created, as I understand it, under the tracks section in Discord. It's called GHC Track Discussion, and that's the place. That's the place to ask questions about this talk. So hopefully you see I just posted here for questions in that spot. So today's talk, I want to give a quick high-level overview for how to extend GHC. And so let me jump into these slides here. Okay, so in this talk, what I'm going to do is I'm actually going to write a new extension to GHC in 30 minutes. But the goal of this is to give a high-level overview of GHC's front end. So I'll define what that is in just a moment. But it's the goal is not to get all of the details down pat. So there's going to be some functions that come up and other things that happen as we see this that maybe you're not going to know exactly what's going on. That's okay. That's expected. The goal is to give you sort of enough clues so that if you were to try to do this yourself, maybe going back, reviewing this talk, something like that, you could just sort of find enough starting points that you could then do more exploration on your own. Two links that I just want to make sure to have in here that I think are really important material if you do want to start hacking on GHC. So this top link it's an article that the Simons wrote about 10 years ago. It still describes the pipeline in GHC. So some things have evolved, some of the names have changed over that time, but it's still, I think, a very, very good introduction to getting your head wrapped around what really is GHC doing. The second link is the active GHC developers wiki. And this is the place to go to learn where to get the sources, how to configure your machine, how to actually do the building, all of that stuff. Again, I'm going to try to avoid those kinds of details in this talk because everyone's machine is different. There's all of these details out there that we don't need to get into. But we do strive to keep it up to date. And it's sort of the ground zero for information for how to contribute to GHC. So before we get to the code, I want to review the GHC pipeline. So we start with a string, right? This is the file on disk, and then that goes through the lexer and the parser. The lexer is written using Alex, the Haskell tool, and the parser is written using Happy. And then that produces this thing I'm writing here is hsyn GHCPS. Well, after we parse in the string, there's actually the Haskell syntax is very complicated. So for example, we have expressions and we have types, and those are going to be different types in GHC. There's going to be one type for expressions, one type for types. Most of those have this HS prefix. And so when I say hsyn, that's sort of a meta name that includes HS expr and HS type and things like pattern matches and patterns and all sorts of other things that we might write in a Haskell program, declarations. Then this type is indexed by either a phase or a pass. I sometimes slip between these words. We'll consider them to be the same. So GHCPS means this is stuff that has already been parsed. PS stands for parse. And it's part of GHC. So the idea with these this type parameter is that this abstract syntax might be used within GHC, but we also want these same data types to be used elsewhere. So they may be in Haddock. One day we hope template Haskell will use these data types. Haskell source X, all of these things might one day sort of adopt all of these data types. So this is using this technology called trees that grow. If you search for that, you'll find various papers on the subject. And the idea here is that we want this particular version of this that's suitable for storing information that's come out of the parser. Then we're going to rename. This is where name resolution happens. And after renaming, we get to HSN GHC RN. And so, again, this is the same data structure, but now it's tailored slightly differently to be suitable for post-renaming. So now we have a little bit more information about names and some other things, like free variables are stored here. Then after we rename, we type check, right? So this is when we find any remaining errors in your program, and that produces HSN GHC TC. And then after this, we desugar, and then the desugar produces core. So again, in core, there are several different data types involved. I've just chosen core expert. And then core expert is what's used in what I'm calling the middle and the back ends of the compiler. So the middle would be all of the optimizations. So what GHC does is you take this core expression. This is a much simpler language than Haskell. And in that simpler language, we can do all kinds of optimizations. And then when that's done, we can actually generate code that runs on whatever architecture you're compiling for. So that's the middle and back end. We're not going to talk about that at all. We're really just going to focus on these front end pieces. So with that high level introduction, let's jump to Emacs and actually start implementing. Okay, so here I've gone over to Emacs. And thank you. I can now see Discord over here. I can see people posting the links. I appreciate that. I can make the slides available after the talk, yes, although there's not much on them, and that's the last slide. So following sort of good practices, let's start by actually creating a test case that we want to be able to work. So we're going to go into the GHC test suite. I'm going to put this in the compiler, in the type checker, although it's not very clear why. And we'll see why I call it this. Oh, why is this already here? It says no longer exists, but it loaded my buffer. In any case, this is what I wanted to type in, so that's fine. Maybe if I do that and then save it is probably a good idea. So here, the idea is I'm making a new form of expression called default. And this is already a keyword, so that's quite convenient to do a quick extension. And the idea is that it's going to look in a data type that we already know. So notice that false and nada here both have type signatures. And find the first nullery, no argument, constructor and use that. And so the idea is that when this program compiles and runs, we will then see false and nothing get printed out. So now that I've typed this in, I now have to go and edit the this all.t file to tell the test suite that I want to run it. So default E and compile and run. Documentation on how this works is all in that wiki. And so now that I've done that, I can go into this directory, and if I say make test equals default E, lots of stuff happens, and then we get a failure. And if we go up to the failure, we get parse error on input default. That's exactly what we should expect, right? The default keyword can only be used at top level. We can't just put it in an expression. So that's exactly what we expect. So let's go and try to fix that. I am going to go over now and go into compiler, GHC. Let's look at the parser. And because I did a little pre-cooking, I happen to know that the thing to edit is AXP2. So I'm going to search for that here in the parser. This parser is written using happy syntax. It's basically very glorified BNF form syntax. It's actually not that hard to sort of go through and figure out what's going on here. So the reason I know it's AXP2 that I want is because this is the one that contains variables and constructors. These are sort of atomic words that I can write in code. Here, I want to add a new case, and that case is going to be default. And over here in the braces, I have to say, after I parse this, what we're going to produce as the abstract syntax for this. Well, we don't have anything there yet, so let's just do something else. Let's just do that. Right? We want to see if it will parse, even if we don't have anything to parse into. So let's see how this works. I will now go to the right place and build. And so while this is building, I will look over and to see any questions. So are we going to tackle polymorphism? No, we are not. That would be very cool, but I could not do that in 30 minutes. Oh no, so we have an error. It says the grammar has 302 shift-reduced conflicts. This is different than the number expected. So why do we have shift-reduced conflicts? Well, because we can have a top-level template Haskell splice expression, and that might look like a default declaration. I don't feel like dealing with that right now, so I'm just going to comment this out. And that means no matter how many shift-reduced conflicts we get, everything will be well. So I've made that edit, and now we do this. Now, of course, if I were really going to submit this as a GHC patch, just commenting that line out would be no good. But we don't want to get stuck spending a whole half hour on shift-reduced conflicts. So let's see. So this is compiling. Hopefully it shouldn't take very long. It doesn't. There we go. That's the sign that it's about to end. Okay, so now we've recompiled. I go back to my test suite here, and then if we go back a few lines, I'm going to run my test again. And if we look up, we have failure. And the failure is hi from Zurahak. Excellent. So that means that we have successfully parsed this test file, except that once we parsed it, we didn't know what to do next. And so we just had this error, but that's exactly what we wanted at this stage. Yes, GHC has over 200 shift-reduced conflicts as a starting point. They're all documented. If you look in the file, every single one is documented, exactly why we have it. Okay, so now what we need to do is we need to have something that we can parse into. So what we're going to do is we're going to edit the abstract syntax type within GHC to be able to store this new expression form. So all of these are stored in the HS directory. So we're going to go into HS expr, and here is the HS expr data type. So we can see in here, this declares all of the different forms that we expect in Haskell expressions. So here we have hsvar, that's for regular variables. We have things like, here's lambda case, here's regular lambda. We'll have all the different forms. So what we're going to do now is add a new form for this default expression. So I'm going to call it HS default E for expression. And here you'll see that all of these different constructors, the first field for each one is one of these X fields. And the idea here is that we might want extra information to be stored in our abstract syntax, depending on what our particular needs are at the moment. We have a convention that every constructor has one of these, and these are actually type families that look at what phase we're in and include either information or not include information, depending on what we find there. So I'm going to make a new one, X default E, and pass in the particular phase. At this point here, I would write if we needed any other information to describe this default expression. But as it turns out, default is very simple. It's just the keyword default, so we don't need to worry about that. I do need to declare this type family. That goes in this file extension.hs. And so let's look for type family xvar, so it can be near its friends. There, I've declared the type family. And then now we're going to need to go back here and then look for its instances. And so we're going to say default E. Well, I don't have any extra information to include. So we say no extension. We're not going to store any extra extensions here. So I'm going to be compiling in just a moment. I see questions bubbling up, and I will tackle those while compiling. And actually, if I save this, I think now is actually the time I'm going to compile. So let's jump back to the correct directory here. And, it's not what I wanted to do. No. I want to do that. Okay, so it's going to start compiling. Let me see, questions. Yes, thank you, Taylor. Phase is like parser and then renamer and then type checker. So as it passes through the compiler, we're going to do different phases. What is this repo? Is that the GHC source code? Yes, it's GHC. Someone's already answered that. Thank you to those of you helping to answer these questions. Yes. Okay. It looks like most of these questions are being answered. Oh no, we have an error. Pattern matches are non-exhaustive. So I configured my make settings here to give an error when we have a pattern match failure. So let's see here. We have one on line 1169. Oh, well, this is something that checks, does an expression need parentheses? Well, a default expression, that doesn't need parentheses. So we're just going to say no to that. And then if we go up here, oh, there's another one, line 929. And this is for pre-printing expressions. Well, that's easy as well. We just want default to be printed out. Okay, let's try to compile again. And hopefully this goes a little bit further. Yes, it is continuing to go. Okay. Let's see. Is the type classes were introduced and described in trees that grow? Yes. That's true. I don't have a link to that. If someone wants to find a link to that paper and post it, that would be cool. Okay, so we got through a few modules, but now we have a problem here. Another non-exhaustive pattern match. It was in TC types origin. And so here we start to see the joy of refactoring, of making changes to a program in Haskell. We just have to make one change, and then we just follow the errors. It's very, very easy. So I go here to line 479. So this data type that we're producing here, so this produces a CT origin. And this data type, it describes things like when you see arising from a use of show, as opposed to arising from a deriving clause or something like that. This describes that. And so because a default, we could imagine something arising from a default, we're going to have a case here. It's going to be a new, so we'll have a default expr origin. And then that's in the CT origin type, which is defined in this file. So I'll just add a new case here. Oh, not foul of a comment there. And then we have to be able to print it. So hopefully that file is now sorted out and we can continue to build. Okay, so the next step that we're going to have to do, this is going to take a little while before we run into the next problem. So the next thing that we have to think about is we've now been able to parse this. We have some abstract syntax for it. So what's going to happen next? Well, we still need to be able to do all those other parts in the pipeline, right? We need to be able to rename this expression. We need to be able to type check this expression, and we need to be able to desugar this expression. So we can start thinking, what would it mean to desugar one of these defaults? Well, I said that I wanted it to be a nullary constructor. So that means desugaring a default should produce a use of a constructor, sort of like I had typed false or nothing. So in a moment, when we get to, we'll see exactly where the error comes up, and then we can start to edit that file. But we'll see that that's indeed what we're going to want to do. Let me see if there's other questions here. Shouldn't happen origin. Yes, some things shouldn't happen. So GHC ID, I believe it is possible to use GHC ID with GHC. I am very slow to adopt new technology, and so I have not yet spun that up on my system. In fact, I only got git gutter working, I think, yesterday. Here we go. So there are, in particular, Matt Pickering has a bunch of tips and tricks for more effective GHC hacking, and I'll just point you to Matt Pickering as a good source for those ideas. I am not a good source for those ideas. Okay, so we have another non-exhaustive pattern match, this time in HS to core in Expr. So this is where we desugar expressions. Line 261. Okay, so this makes sense, right? We don't know how to desugar this. So we have to have something here. But now I'm stuck a little bit. So if we go back, let's go back for a sec and look at our test case. So in our test cases, we know the type of the expression, and we're going to use that to inform what the expression actually is. But now, when we desugar, we need to know the right constructor to use. So the problem here is that we need to be able to communicate from the type checker to the desugarer in order to be able to sort of know how to desugar this. That's exactly what these extension points are for. So what the type checker is going to figure out is what the correct constructor is. And then the desugarer is going to use this information. So if we go back to the desugarer, I'm now going to say that this extra piece of information in this phase is going to be a data constructor. But now, even if I have a data constructor, how do I deal with that? Oh, look. Down here, this is hscon-like out. That might be relevant. So let's see. So if we look at dscon-like, it does ds-hsvar datacon rapid DC. DC probably stands for data constructor. So let's just steal that line of code. That looks convenient. And then we go back up. Where is it? Oh, I've lost it. There it is. Okay, let me fix the name there. And so that has to be a constructor. Okay, good. Now we have to go back and change that type instance to be what we want it to be. We need it to store a constructor, not FHS, X default. There it is. So now what I want to say is I want to say type instance X default E GHC PS is no X field. We don't need any extension after the parser. We don't need any extension after the renamer. But after the type checker, we do need to store a datacon. So that extra extension field now is going to be really useful for us. So with that change, we can start compiling again. Oh, it's not in scope. That's easy to fix. And then build. Okay, it seems to like that. So it's gonna chug for a little bit, and we can see if there are questions. Yes, there's lots of stuff happening here, but a lot of them are being answered. Okay, so I'm going to jump ahead. I'm mindful of the time here. So what this is going to do is this is going to eventually compile, and it will actually, if I remember correctly, run this time, but with a failure in the type checker. And so I'm just going to jump ahead and start editing the type checker. In the type checker, there's actually sort of two parts to the type checker. The GHC type checker works by doing constraint generation and then solving. And so the part that we're going to be interested in is the generation. This is the part that actually looks over your source code. And then it creates a bunch of constraints like int equals A and B equals list of C. And then we maybe learn about C later. And then those get solved. So if you're interested in learning more about the constraint solver, I'll highlight my colleague Nick Frisbee's talk on constraint solver plugins. And you can learn more about them there. Also, this idea of adding an extension to GHC, is, if you want to learn more about that, you can see a real extension in qualified do presented by a different colleague, Facundo Dominguez. And these are all ZeroHack talks that I'm highlighting. And then there's a much larger extension, which we believe is on its way to being merged, is the linear types extension, with which hopefully we hope will make it for 8.12. And my colleague Devesh Otwani will be presenting about that during ZeroHack. Okay. So getting back here, so we want to go into the generation part, and we're going to look at generating expressions. And here we have each case. So in the TC expert case, for HS default E, and we already know the result type. And so here, I apologize, I'm going to have to do some stuff that I'm not really going to explain in much detail. But we're going to say that this res tie is an exp type, and I don't want it to be an exp type, so we have a conversion that changes it to a regular type. And then I want to see, is this a regular tycon, something like int or bool, as opposed to a type variable? And if it is, then we can extract out the tycon. But we also need that tycon to be associated with some datacon. So this checks, is this an algebraic tycon that has data constructors? And are any of them nullary? We can only work with nullary tycons, nullary data constructors here. So we're going to filter null datacon org argties. This gives us the datacon org argties gives us the list of arguments. So we're going to use that to filter. And if we find one, then great. Now that means we can succeed. And to succeed here means we have to call this function tc wrap result. And I need to name my initial expression here because tc wrap result takes it for error message purposes. The type checked expression is going to be an HS default D, but now I'm going to stick my data constructor DC in there. Then I have to give the type of this. So that's datacon user type of DC, and then the original type that I expected. Otherwise, we're going to fail. Now, I would like much better error message than that, but we'll accept it for the time being. Okay, so that will do the type checkery bit. And then I see that there was an error here, whoops, in HIE file generation, line 1035. So this is a fairly recent addition to GHC that gives extra information for use in IDEs. It's a really fantastic development. But for now, we don't really need to include information about these default expressions. So I'm just going to sort of do a trivial thing. That was just an accident. Didn't mean to do that. Okay, let's keep compiling. Should be very nearly done now. And while that's going, so this also, I think, would probably get there. Oh, driver main. That means we're very near the end. But there's one step that we've skipped, and that's in the renamer. So let's jump over to the renamer and rename expressions. Oh, it compiled, finished. Still doing a few things. Okay, so here we need to edit rn expr. And how would I know that, by the way? Oh, here, it's done. I can show you how I would know that. So if we go back to the test suite and run our test, then we would see here, still says hi. Oh, we never updated the parser. Never updated the parser. That was very silly. So here I'm going to sort of copy the code that's immediately below because it looks reasonable. That should work to generate an HS default E node. But as I said, we have to still do the renamer. But the renamer, that's really easy. And the reason that we didn't get an error before is if we look at the end of this RN expert that does this big pattern match, it has a fall through case, which is probably poor programming practice. But if I do this here, well, there's nothing really to do to rename one of these things. There's no free variables in it. So I can just return another HS default E with no extension. And the renamer also does free variables. So we need to say that there are no free variables in this expression. So now if I build this, I think that's it. It builds. And then what happens in my dear test case? Fails. Oh no. Oh, I forgot about zonking. How could I forget about zonking? So if I search for zonk expr, I see that there's a catch-all case to this zonk expr function. So we could just do a search and find that. Zonking in this case does not need to do anything. This is, again, something that only happens when you have sort of big nested things that you have to worry about. Okay. And compile, compile, compile. Okay. Just looking at questions. Yes, I forgot about zonking. And here, now I run the test. Happy to explain zonking if someone asks a question about it. Aha! The test fails because it's unexpected output, but indeed the output is not unexpected. It is what I expected, but the test suite did not know that. So I just say make except, and then we are done. So that's a quick how to implement an extension. We bounced to a lot of files. I didn't explain lots of what was going on. I know that. But again, the goal here was just to sort of show the different moving pieces that you would have to think about. And each one of these is documented on the wiki. There's other resources to use. And I think we'll end it there. And I can take some questions. I think the next talk is still over 10 minutes away.
Thanks a lot. We have a few minutes for questions.
Okay, so let me, what should I do now? Let me turn off screen sharing. Can I do that? And then I will move, oops, this over here. Okay, cool. Wow, Athos, what on earth is that? How did you do that? It's an emoji with a Haskell logo or something. I'm going to upvote that right there. So let's see, I see a bunch of people typing, maybe some questions. And Haskell, can I do that too? Wow, that's very cool. I feel I just witnessed an intense demystification session. I'm glad it's demystification and not mystification. Okay, explain zonking. Oh, good. So let me just say the bandwidth was a bit too high. I thought about that, and I would not have given this talk in a live format. This is something I think unique to the remote format, in that I know everyone can really easily go back and re-watch certain parts of the presentation, and so that you can get some more, you can sort of see things happen a little bit more slowly if you want to. That's actually very intentional on my part. I would have never done this actually live in the room. Okay, so zonking, when you, after type checking, we sometimes have the process of type checking solves for variables, right? So if I say length, here, I'll just type in the window here. If I say length of true false, right? So if I say that, GHC has to figure out that these are bools. And to do that, it says, okay, well, the type of these things is going to be some variable A, some type A. We don't know what A is. And then later it's going to discover, A is bool. So what that does is that in my AST, there might be an A stored somewhere, and I later learn that it's bool. Zonking is the process of walking through the entire AST and replacing all of the A's with bools. Can we see your final diff somewhere? That's a really good point. Yes. I will post that. I don't know where yet, but I will post that.
All right. Thanks a lot, Richard, and thanks everyone for the discussion. Maybe at this point, let's move the discussion over fully to Discord so we can set up the next session. We also have a voice channel called GHC where you can also have a voice chat if you like.
So this is the GHC voice channel? Is that what it's
exactly,
called?
Yeah,
okay.
GHC-voice,
okay.
Yes.
I will pop over there as soon as I... yes, zonking is substitution. Okay, thank you so much, Andreas, for inviting me and for hosting this. And enjoy ZerHack, everyone. I'll see you around.
Thank you. Enjoy ZerHack, everyone. And thanks again, Richard, for the great talk.
So long.